So today I'm gonna continue basically on some of the topics that I have been presenting at the previous two webinars. And previously I talked about how an enterprise end-to-end configuration can link between the engineering side of the organization in the product definition and where products get designed and engineered, to the sales side of the organization, where the products are being offered to the market, being sold, websites, CRM systems, linked down to manufacturing, and finally to service and upgrades and maintenance. So those are the four key functional areas that we typically deal with when we build the configuration solutions. Today, I'm going to focus on the VT circle in the middle of this picture. You could say that the way to achieve such a solution, and what we talked about before, is that we have to bring together all the rules from these different functional areas. If we keep them in separate systems, in separate silos, it's very difficult to get a consistent and aligned view on the product. Engineers may think that they have to engineer combinations that are being ruled out later in the sales tools, for example. We talked about how rules can be authored in a centralized system, or they can be brought in and combined. Some rules might still be maintained in engineering systems or in other systems, but they have to be combined into a single complete rule set. That's one half of the solution, you could say, and it certainly is an important step. But the second step is that you have to have technology, you have to have a configuration engine that can handle the fact that now you have brought together all these rules in a single system. I'll talk about what is the fundamental configuration problem that we are addressing, and in very short, I will go through our VT technology, our way of addressing the configuration problem, and then I'll go into 5 areas where you can see how having a strong configuration engine can immediately give some business benefits. So as you may know, Config.it has been around for about 20 years, and we have, during those 20 years, we have based everything we do on our VT technology. So before I explain to you what that is and how we solve the configuration problem, I think it might be useful to be clear on what is the configuration problem. This has nothing to do with Config.it. This is basically any organization that deals with configurable products, or maybe even just deals with some parameters that are linked by rules. They will have a need to solve the configuration problem. So basically, the problem is that you have a model. We call them product models. This is a logical representation of a configurable product, and it has two things. It has variables, or sometimes called features, sometimes called options, and it has some rules that link these together. So that's basically what a product model is. And whenever you have a configurable product, you need to create one of these models, and you need to start arguing about it and using it in different processes. It could be a CPQ process where you need to configure and price the product. So the fundamental challenge is to have a interaction with a model where you can guide a user. So that's what a configurator does. It uses the product model. It uses these variables and the rules, and based on that, it guides a user to find a valid configuration. And a key point is that it should help a user to find such a configuration. I don't have the time here to go into all the fundamentals of this problem, but it's interesting to notice that even the most simple question you might ask of such a model, namely, can we find a valid configuration? Does that valid configuration even exist given a model? That problem is a known difficult problem. So it's mathematically provable that this problem is difficult for a computer to solve. And if you are in computer science, you can look at different problems, and sorting, for example, is a very simple problem for a computer to solve. It's very efficient to sort numbers. It's very easy for a computer to do so. So the picture here on the right illustrates that different problems have different runtime behaviors, and so that means how does the runtime behavior behave, or how does the runtime of the computer algorithm perform as you grow the size of the problem. And unfortunately, you could say that this configuration problem, the fact that it's this NP complete thing, it basically means that worst case, we're going to hit an exponential in the size of the problem. And there's nothing we can do about that. That's purely the nature of the world of how this problem is. In order to find out whether there's a valid configuration, we basically have to list them all out and try them all. That's the best we can do. So how do we solve this problem? This has been around for ages. You can see here that I've listed some of the typical approaches to solve the configuration problem, and they date all the way down to early 70s. And I also listed some different commonly known configuration engines on the right here. And we typically classify these approaches in these three categories. We talk about the rule-based systems or production-based systems, and there's a common system for that available on the net today called Rule. We have constraint-based systems, and there are two subcategories of that. There's something called constraint propagation, which does some of the configuration problem, not all of it, and there's constraint solvers that do all of it, but have some challenges. And then we have the compilation-based technology that is what Configured has been developing and evolving over the last 20 years. And those are basically what's out there today, and they all are trying to solve the same problem, giving a model. How do we guide a user to select choices for the different parameters, variables, features, so that all the rules are satisfied? Yeah. So how do we address this problem? Well, we have an approach which is a two-phased approach. We have a compiler that takes the rules in whatever shape and form they have, and we calculate the set of all the possible configurations that are legal. So we create this representation in the middle here that we call the VT file or VT representation, and it is a representation of all the valid combinations that the rules define. And once we have that, we can use that representation, for example, to drive a configurator that can interact with the user, and at the end of that process, come up with a valid configuration. And just to illustrate the power of this technology, if we have some statistics for one of our customers, they had a model with 8,000 features in the model. It had 1,800 rules. It has 10 to the 50 possible combinations, and still this representation of the valid representation was just a 3 megabyte representation. So it's a very compact representation of a very large set of combinations. We typically say that we solve the difficult problem once, and then once we have it, we have a very easy way to calculate the response that we need to do when we're configuring it. Another way of illustrate this is that we can use this representation. We can use it for configuring, but we can use it for many other things. So I didn't mention in the previous slide, there was a link to what we call binary decision diagrams. It's a data structure not invented by us, but by a guy called Randall Bryant back in 1986. And this is the data structure that everything we do is based on. We have evolved it over the years, but a binary decision diagram is a strange looking thing here in the middle. And this is where you could say this is a very compact representation of very large solution spaces. And it's not human readable as such, but what we often do is that we can export or generate an explicit solution space and illustrate it here on the right as a table, as an Excel sheet for that matter. If you select the variables, we can efficiently generate all the valid combinations of those variables. And this, as I will show you in a moment, will be quite useful when doing different types of optimizations and analysis. So it's just, the point here is that even though we have this weird representation of a very large number of combinations, it says 10 to the 29th here, it could be 10 to the 50, 10 to the 100, but still we can take this and we can what technically is called project it down to selected variables. We can basically generate those And they will be a small number, because there's only, if we select 5 variables, there will only be so many possible combinations. So that would not be a very big problem to generate the representation on the right, and that's quite useful. So I want to go through 5 areas where we see a strong benefit of this compile-based approach. And I will start with the most basic capability of a configurator, and that is that it can guide a user to a valid configuration. Now, you could say the business benefit of this is basically that this allows you to expose configuration models to people who do not necessarily know the technical details of the model. Because if you're an expert, then the configurator, it's okay that it doesn't guide you very much, but purely basically validates that your choices are valid. But if you're non-expert, then you need the full guidance of a configurator. It needs to make sure that it doesn't lead it down to a path that at some point turns out to be invalid. And this is actually not unusual for configurators to allow the user to select combinations that at some point later in the configuration process, it suddenly discovers that this will be an invalid configuration, and it basically says, sorry, now I'm invalid. Please go back, change something 1, 5, 20 steps back, I don't know, but something has to change, and then you can try and go down a different path. This sort of trial and error will not work for non-experts. They will not know what to do, and it will be an extremely error-prone and frustrating experience. At a very basic level, this looks like this, that you have when you have to choose a parameter, whatever this is, a number of gears on a bicycle, or the number of floors in a building, or whatever. The configurator will have to be able to guide you. It has to be able to tell you that even though you have selected a value right now, in this case 21, there are other choices that are also consistent with the previous choices. So in this case, the value is 3, 4, 6, 7, and so on. And of course, this is the way the UI looks like can be determined completely independent. It doesn't have to look like this, but this is very typically that you gray out the combinations that you do not allow. And it's important to understand that when 27 is highlighted here as in white, it means that I can choose it. And of course, it will have to be consistent with my previous choices, but it has to be the case that I can continue configuring and actually complete my configuration to the end and get a valid configuration. That's what this white color means, that I can find values for all the remaining parameters in my model, all the other features, and they will actually it will actually be possible to do so. There are also some gray values in this little drop down, and they indicate choices that I cannot get. And this you would expect from a guidance configurator, that if I choose this choice, that the configurator can explain to me what the consequence of doing so, basically which of my previous choices that are in conflict with this one do I have to remove in order to be able to get this particular choice. If I really wanted to have the 5 selected, what would I have to remove? And again, the user, he doesn't know the rules. He doesn't need to know that these are the 5 rules. He needs to know what choices that he has to remove and being able to optimize on that. So this is, I think, one of the most fundamental properties of a configurator, that it can help a user to find a valid configuration. Very closely related to this is that of performance. One thing is that you have brought all your rules together in one system. Another thing is that you can give it to a configuration engine, but if it doesn't answer efficiently and quickly, it will never get any user acceptance. And there are some typical guidelines out there on what does acceptable performance mean. And the typical guideline is anything less than a second is acceptable. If it's around 0.1 second, 100 milliseconds, it will feel instantaneous. If it's less than a second, it's okay. About a second is where people's patience stop. Remember, we talk about a second from you select a choice to get a response back from the configurator. If that round trip is more than a second, people are going to be very, very annoyed with your application. And the benefit of having a compiled approach is that we solve, so to speak, the difficult problem once. Whenever you change the rules, you have to do a compilation, very similar to how you develop software for that matter. You write your code, you compile it, and once you have compiled it, it's very efficient. But the compilation itself can take a little time, and we typically talk a minute or so. But once you have selected this or compiled this model, then it is available as a representation in this VT representation, and the interaction with the configurator will then be in the millisecond range. We typically have very efficient, very quick. It's very much like a lookup in a table to guide the user to find the consequence of his choice. So we have solved all the hard problems in this compilation phase. Now we have something that can guide you. We have something that's fast. Another topic that is very important and is a big challenge for many organizations, that is to make sure that the rules that you create are actually correct, and make sure that whenever there's a change to the rules, that they are correct, and making sure that you validate that before you release that rule set to downstream systems. So it's quite bad, of course, to have invalid rules on your website or in your sales tools, because that allows people to configure invalid configurations and order them, and that causes all kinds of challenges of being able to handle those errors in the ordering process. So we have to make sure that these configuration models are correct before we release them for our downstream systems. Now, how do we do this? Well, a very typical approach is that you simulate a model. And the thing about simulation is that it doesn't work. The number of combinations that are out there, and I put a car up here, it has, this particular model has 10 to the 21 valid configurations. It's a very, very large number. And this number means also that it's very, very difficult to test. It will only, if you simulate or test through going through a configuration process, it will never cover any small fraction of this very large solution space. So what you have to have is that you have to have a way to validate the changes at a higher level. You cannot just go into a configurator and try out, now I choose Sweden and see that my changes work for Sweden, and then I had to go to Germany and see that it still works for Germany. That simply won't work. So the fact that we have a representation of the full solution space allows us to do some pretty cool things. For example, we can create reports that compares the solution space from one previous time to an updated rule set. And we can highlight all the changes that might have appeared in that update. So that allows us to, for example, say, well, there's no changes in Europe, but your rule changes have this and this and this effect in the US market. We can also use the fact that we have the whole solution space to prove properties, and we build that into our tools that you can set up properties that you would like to have validated, and whenever there's a change in the system, the application will revalidate that all those checks are still holds true. So this allows us to have comfort that a change haven't broken something fundamental in the model. One thing is to have product models and making sure that they're correct. But once you have configured the product, that configuration is combined with a bill of material to create what we call the unit BOM. So that's the process that we have tried to illustrate here on the lower left, that we have a configurable BOM, sometimes called a super BOM or a 150% BOM. This is a bill of material that has selection conditions to filter and select the right parts depending on the configuration. So the process is very similar to, or is very simplified, shown here. that we have the generic BOM, the configurable BOM on the left here, but then when we apply the configuration that has come out of the configurator, it results in a order specific BOM where we have filtered out those parts that matches the particular configuration. Now this process is of course essential to get correct. If you get a unit BOM here which is invalid, a car with 2 engines and no wheels, as an extreme example, then of course you're going to get all kinds of problems in the manufacturing process. So we have to make sure that the bill of material matches the rules in the product model. Otherwise, we might accidentally create configurations that doesn't match to the bill of material. And this is what I've tried to illustrate in this diagram on the right here, that if you look at what the bill of material is defining, that's in a sense is what we call buildable configurations. The blue circle is the orderable ones. Those are the ones that are allowed by the configurator, and then the actual ones that are sold is some subset of those that the configuration logic will allow. And this picture illustrates some problems. For example, there's a big area on the buildable configurations that cannot be ordered. That of course is a problem because that in a sense is wasted. It's over-engineered. There are parts and combinations that have been engineered but cannot be sold because they are not allowed by the configuration logic. And there's also a problem here that we have that the allowed configuration by the configuration model goes outside of the gray buildable configurations, and that means that we allow configurations that we cannot manufacture. So these situations have to be avoided. And the nice thing about having the full solution space is that we can combine information from the bill of material with information about the valid configurations. And in one process, we can identify whether one of these situations occur and create a report with counterexamples. So this allows us with comfort to say the configuration model will never allow combinations that we cannot manufacture. And again, this avoids errors in the manufacturing, errors in the ordering process where we have to go back to the customer and say, sorry, we cannot manufacture what you ordered. The last item I want to talk about, and again, this will be very quickly, these are fairly big areas, so it will be just a quick tour through them, but an area that we have also started looking into is that of optimizing the bill of materials. So one thing is to make sure that the structure that's there is aligned with the configuration model, but we are also interested in looking at whether the variance that we have is necessary. Can we remove parts in our bill of material that will only remove a small fraction of the actual choices in the configuration model? And sometimes that analysis is called low runners, as those that are very infrequent or very low percentage of the orders will trigger. And this is best illustrated with an example. Here's a particular part. It's a part of a car. It sits right behind the steering wheel, and it has these different controls. And depending on how you configure the car, this part will have certain controls or may not have them. So we can imagine that you have a car with or without the lane assist. That's an add-on option. You have to buy that. It might come with or without the adaptive cruise control. Again, that requires another control arm on this part. There might be something about the steering wheel heating. If you have that, that requires a particular wiring in this part, and so on. So there are these variant drivers that all have an influence on the part. And what turns out is, when you look into this, that there might be, and in this example, there were 96 physical parts that all dependent on these variant drivers. Now, you can ask yourself, is 96, is that too many, or can we reduce this? And in order to answer that question, what you can do is that you can look at take these variant drivers, and these are shown as columns in a feature tree, and now you can combine this tree that leads to each of the 96 variants on the right here. You can combine that with statistical information about the probability of a customer choosing each of these choices in the tree, and that will end up in a probability for each of the variants. And now you can put some limit on and say if they're less than 1%, we draw them red, and that will mean that you get some of these parts identified as the low runners. And the next natural step then would be, okay, now we have identified these, what do we do about it? And the way to get rid of them is you add rules in the configuration model. For example, you bundle things up, so you can only get the lane assist together with the adaptive cruise control, and by doing so, you basically eliminate some of these, the need for some of these parts. 25 quick minutes about how we can see that the configuration engine directly influences some of the business value you get out of a configuration solutions. And I've been through, and I know this is going very quickly, and of course we can take a more detailed dialogue if necessary, but these are some of the areas where we see where our technology is helping our customers to get these benefits. So with that, I would like to open up questions. So the question is whether we can handle continuous variables, and by that is meant numeric variables that can, like real numbers, a length between 0 and 1,000. And the short answer is yes, we can do that. But we don't do it. We actually have additional solvers on top of this compiled approach. But we do certainly do handle any kind of arithmetic and mathematical operators as square roots and cosine and things like that. That's fully supported in our engine, but it's not done by this compiled approach. We have to solve that outside as a hybrid of the two. So we actually do have both constraint solvers and the compiled approach, and we combine them. From the outside, you can't tell the difference.
Which user guidance can be done in regards to pricing?
Yeah, so pricing is a completely additional topic, and I think the question is about how can we, if you want to optimize the price, you want to configure the product, and then you basically say, please give me the cheapest from this point onwards. And it's not a straightforward thing to do. In our configurator, we have knowledge about what features are priced and which ones are not, and we use that in the you can set it up so that it by default chooses the non-priced features, what we call the less features. Otherwise, what you need to do is that you need to query the pricing engine and search for the lowest price. It's not a simple problem to solve because the pricing typically is very non-linear. So it's not like the price is a sum of the price for the options. There are all kinds of dependencies in the price logic.
I have another one here, and then I think the rest we might have to take offline. How does your tool interface with a PLM system? The reason being that all BOMs will be managed and mastered in PLM system.
And that's very true. And we are building integrations to PLM. We have a service that can do this BOM validation, for example, and that service will have to be called from the PLM system. And we are working to integrate. We have over the years integrated to almost all the typical PLM systems, and it's absolutely true. The bill of material and the selection conditions are being mastered in the PLM system. The configuration logic sits in our system, and you will have to do an integration between the two to get this BOM validation to work. We're building standard integrations to some of the common PLM systems, such as ours. So with that, I think we'll say thank you to everybody.